Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 7, and it is entitled Average Speed and Average Velocity for Linear Motion, Average Acceleration, and Pressure. Your authors have chosen to address multiple topics in this lesson, and we'll look at each one in turn. We begin with average speed and average velocity. For most of this course, we'll describe the motion of objects as if they are single points. In reality, when extended bodies, such as automobiles, airplanes, divers, and most other objects that we encounter in our regular world, when they move, their motion can be quite complex. But it turns out that all motion can be described as a combination of the translation of the center of mass of the object and the rotation of the object about its center of mass. When we say the word translation, we talk about the movement of the object from one place to another. Whereas when we talk about rotation, we mean the spinning of an object about some axis. Rotation is more complex than translation is, so early on in our study of physics, we'll concentrate on the translation part. And to do so requires that we model the object as if it is a single point or a particle. Back in Lesson 4, we examined distance versus displacement and speed versus velocity, distinguishing between the scalar and vector nature of these concepts. When we talk about vector quantities in one dimension, then it is sufficient for us to use signs to indicate the direction of the vector. And we'll take our cue from the math department. Most of the time, when we deal with horizontal vectors, which are parallel to the x-axis, a positive sign will mean that the vector is pointing towards the right, and a negative sign means that the vector is towards the left. And in a similar way, when we deal with vertical vectors, positive signs will generally indicate upwards vectors, whereas negative signs will indicate downward vectors. Now we'll have occasion to use different directions and different signs from time to time. And when we do so will depend on what kind of problem we'll deal with. But in general, this is the convention that's used for talking about signs and directions. Let's also recall the equations that we have for average speed and average velocity. Average speed is the total distance traveled divided by the total time of travel. And average velocity is the total displacement divided by the total time. You'll recall that displacement equals the final position minus the initial position. The sign of the displacement tells us the direction of the displacement according to our mathematically given axes. Let's apply these definitions and work a couple of examples. Let's start with example 7.1. A particle moved along the x-axis from x equals 5 centimeters to x equals 16 centimeters, and then back to x equals 9 centimeters in 2 seconds. A, what was its average speed? And B, what was its average velocity? In part A, we're trying to figure out what the total distance is and divide that by the total time in order to come up with the average speed. Now, there are two segments of motion. The first segment goes from 5 centimeters to 16 centimeters. So if I want to find the distance there, I take the difference between those two. 16 minus 5 is 11 centimeters. The first leg of this trip is 11 centimeters long. And then we have leg 2, which starts at 16 centimeters and goes to 9 centimeters. The distance of leg 2 happens to be in the opposite direction, but we don't care about the direction when we're talking about distance. We just want to know how much ground did we cover. And in that segment, I take the difference again, and I find that 16 minus 9 is 7 centimeters. The average speed is the total distance divided by the total time, and the total distance is 11 plus 7, or 18 centimeters. The total time is 2 seconds. I can do that in my head. 11 plus 7 is 18, and 18 divided by 2 is 9, and the units are centimeters per second. So there's my answer to part A. In part B, I need to know what is my total displacement. I'm going to be a little more careful about part B, and I would like to sketch this in an x coordinate system. So I'm going to draw a number line to represent the motion. First leg of this trip starts at the 5 centimeter point and goes to the 16 centimeter point. This displacement vector would be positive. The magnitude of this displacement vector is 11 centimeters, and its direction is to the right. We would say that the displacement is 16 centimeters minus 5 centimeters, which is equal to positive 11 centimeters. But that's not the end of the trip. I now backtrack in the second leg of the trip. In the second leg, I begin at the positive 16 centimeter point and end up at the positive 9 centimeter point. This displacement vector is actually now 7 centimeters long, but its direction is to the left. And so I would say that this is a negative displacement vector because the direction that this vector points is to the left. Now, what are we looking for? We're looking for the average velocity. So we're looking for the final position minus the initial position in order to figure out what the displacement is. Final position is at 9 centimeters. The initial position where I've started the trip when I started the stopwatch is at 5 centimeters. So the displacement is the final position minus the initial position. So I have a vector that is pointed to the right. It has a magnitude of 9 minus 5, which is equal to 4 centimeters. So a positive 4 centimeters is the displacement. The average velocity is the displacement divided by the time. The displacement is the final position minus the initial position. The time interval, we could call that delta t, which is 2 seconds. So in this case, that's equal to a positive 4 centimeters in 2 seconds, and that's equal to a plus 2 centimeters per second. There is my average velocity. It's a positive number, which means on average I move to the right, and you can see that from the number line. There's the first example. Let's try the next example. Example 7.2. At t equals 12 seconds, the plane was at an altitude of 500 meters. By t equals 30 seconds, the plane had climbed to 1,260 meters. At t equals 80 seconds, the plane had dropped to an altitude of 600 meters. A, what was the average vertical velocity of the plane between t equals 12 and t equals 30 seconds? B, what was the average vertical velocity of the plane between t equals 30 and t equals 80 seconds? And C, what was the average vertical velocity of the plane between t equals 12 seconds and t equals 80 seconds? Let's sketch a diagram. Now, if I have an airplane, the airplane is going to be traveling both horizontally and vertically, but I'm only interested in the vertical motion. So I'm just going to draw a vertical number line and sketch points. In leg A, I have a starting point, 500 meters, and a starting time of 12 seconds. I have an ending point, 1,260 meters, and an ending time, 30 seconds. The displacement vector is positive because it's pointing upward. My starting point is below the ending point, so I have a positive displacement in the vertical direction. Now in leg B, a starting time of 30 seconds and an ending time of 80 seconds, the plane drops from 1,260 meters at the start of that leg to 600 meters at the end of that leg. In this case, displacement vector is negative because the ending point is below the starting point. Now we want to figure out the average vertical velocity in part A. We want to figure out what's the average vertical velocity in part B. And then we want to put those things together and just look at the initial and the final point from 12 seconds all the way to 80 seconds. Let's start with part A. The average velocity is the displacement divided by the time interval in part A. We can put the numbers in. The displacement is the final position minus the initial position, 1,260 meters minus 500 meters during this particular time interval. The time interval is 30 seconds minus 12 seconds. Now you have a calculator, apply it. The average velocity is a positive 42 meters per second. Positive meaning that the object was moving upward during this time interval. In part B, we do the same thing. The final minus the initial position in the numerator and the final minus the initial time in the denominator. And again, we're interested in this particular time interval. Put in the numbers, and I find that during this leg that the average velocity was negative 13.2 meters per second. Negative because the final position is lower than the initial position was. Now, part C. We take the average vertical velocity between the two times that we're interested in. Final position, in this case, is 600 meters, and the initial position is 500 meters. The time interval is from 12 to 80 seconds. And now put in the numbers, and I get that the average velocity was positive 1.47 meters per second. The reason for that is that the displacement was positive in this time interval. Now, let me throw out a caution at this point. You might say, well, I can find the average velocity by taking the two average velocities in part A and part B and averaging them together. Let's see what happens when you do that. Let me take the average of those two numbers, 42.2 and negative 13.2, and let's see what we end up with. And now I'll put the numbers in my calculator. Using that method, I would end up with a positive 14.51 meters per second. And if you were to do that, then you are not going to get the problem correct. The reason that doesn't work is because the time intervals in question are not equal to each other. Those two time intervals are different time intervals, and as a result, you have given them equal weight when you put them together and divide them by 2. They don't receive equal weight when you solve the problem in the correct way. I hope that you don't make that mistake when you come across these problems. Let's now extend our discussion to average acceleration. We will come to see in an upcoming lesson that the concept of acceleration plays a key role in appreciating how the world works. And so we're going to spend a little time introducing the concept here. Acceleration is defined as the change in velocity with respect to time. Symbolically, we say that A is equal to delta V divided by delta T. And while that definition seems to be easy to write down, for many people it's a difficult concept to grasp and understand completely. You've used and you've heard used this word acceleration in various common situations, and so you already have some idea about the meaning of the word. Most typically, when folks use the word acceleration, they mean something that's speeding up. After all, when you drive a car, the pedal you push to make the car go faster is called an accelerator. So this idea of speeding up is a good one, but it's not a complete one. Acceleration is what you feel when you're moving. This is what you sense when you drive a fast-moving car over a little hill, that drop you feel in your stomach as you get to the top of the rise. Acceleration is what you sense when you're going around a curve. Acceleration is what you sense when you come to a sudden stop. And physiologically, that sensation arises from fluid motion in your inner ear. Now, this isn't a biology course, and we won't try to describe all the fascinating anatomy associated with your sense of motion. But anytime you change how fast you're moving, or anytime you're changing which way you're moving, then you're accelerating. It might be that you're speeding up. That's what happens when you mash on the gas pedal. But it could be that you're slowing down, which is what happens when you press on the brake. Or it could be you change which way you're going. That's what you do when you twist the steering wheel in your car. In each of those situations, you are experiencing an acceleration. Let's come back to our equation for acceleration. Acceleration is a vector just as velocity is a vector. When we deal with linear motion, then the sign of the acceleration will tell you its direction. It's possible to have positive accelerations, which means that the velocity is changing in the positive direction. And it's possible to have negative accelerations, which means the velocity is changing in the negative direction. It turns out that whether the object is getting faster or getting slower depends on the relative signs between the velocity and the acceleration. If the velocity and the acceleration have the same sign, then the object will be increasing its speed. On the other hand, if velocity and acceleration have opposite signs, then the object will be slowing down. So just because acceleration has a positive sign doesn't always mean the object is speeding up. We'll get a lot more practice with this in future lessons, so if you don't get it right away, it's not something to sweat too much at this stage. Let's try another example. Example 7.3. An object moving in the positive x direction went from a velocity of 100 kilometers per hour to 40 kilometers per hour in 4 hours. What was the object's average acceleration? We begin with our definition. Acceleration is the change in velocity with respect to time. Now you'll notice that I have not put the arrows above the A and the V. I'm just going to let the signs tell me whether the object has a positive or a negative acceleration. The final velocity, which is 40 kilometers per hour, it's moving in the positive direction, minus the initial velocity, 100 kilometers per hour, divided by the time interval, which is 4 hours. 40 minus 100 is equal to negative 60. The units are kilometers per hour. The time interval is 4 hours. 60 divided by 4 is equal to 15. So I have negative 15, and the units are kilometers per hour per hour. So that means every hour the object's acceleration was negative 15 kilometers per hour. I could write this as a single combined set of units that would be negative 15 kilometers per hour squared. As you can tell by looking at direction of the velocities, you see that the velocities are both positive in this case. The acceleration is negative, which means that the velocity and the acceleration have opposite signs. And because they have opposite signs, that means that this object was slowing down. And that makes sense. You started at 100, you ended at 40. That means that over this period of time, you slowed down. Finally, we come to a completely different topic. The topic is frequently associated with fluids, pressure. Usually when people think of pressure, they imagine the increasing feeling of water pressure on their eardrums as they go descending into the deeper end of a swimming pool. Or they might think of their eardrums popping as they drive up or down a mountain. Or maybe they're concerned with the air pressure in their tires of their automobile. You've heard of terms such as peer pressure and pressure cooker and under pressure and blood pressure and pressure points, all terms that in one form or another derive their meaning from this physical idea of pressure. By definition, pressure is equal to force divided by area. In symbolic form, we use the letter P to represent pressure, F is force, and A is area. So it's a formula. Technically speaking, it's the amount of force acting perpendicular to a surface divided by the area over which that force acts. We'll mostly be interested in gases and liquids, and we'll most frequently compare our results to the pressure that we're most familiar with, which is atmospheric pressure. We live in a world in which we're surrounded by air. As a result of the weight of that air, which is several miles above us, there is a force that's exerted on us as a result of the weight of that air. Your authors contrive several numerical examples of pressure which you're not likely to encounter in a real-world problem. At this point in the course, we just introduce the concept of pressure and get you to make some conversions between common units of pressure, the most frequently encountered of which are in atmospheres and torrs and psi, which stands for pounds per square inch, kilopascals, millimeters of mercury, and bars. So the kinds of problems that you'll encounter are going to be exercises in applying conversion factors. So here are the equivalents. I see I failed to add to the list kilopascal. 101.3 kilopascal is equal to 1 atmosphere. Incidentally, the torr is named after Torricelli, a student of Galileo's. Kilopascal is named after Pascal, both men involved with the study of pressure. 1 atmosphere is equal to 760 torr. That's equal to 14.7 pounds per square inch. That's also equal to 760 millimeters of mercury. That's equal to 1.013 bar. And that's equal to 101.3 kilopascal. So let's try a numerical example. The atmospheric pressure in a certain altitude is 735 torr. Convert this pressure into A, atmospheres, B, kilopascal, and C, newtons per square meter. Let me remark here that the SI unit of pressure is Newton per square meter, and that is sometimes referred to as a Pascal. A kilopascal is equal to 1,000 Pascal. A Newton per square meter is the unit that we'll need to work problems in if we need to make calculations involving other metric units. All right, so we begin with 735 torr. We want to know how many atmospheres this is. So we need to know that there's 1 atmosphere in 760 torr. I pull out my calculator. I find 0.967 atmospheres, a little less than 1 atmosphere. In part B, we want to convert to kilopascals. The equivalent is 101.3 kilopascal per 760 torr. Now use your calculator. Just under 98 kilopascals of pressure. Now part C, a Newton per square meter is the same as a Pascal. And if 1 atmosphere is 101.3 kilopascal, that means that 1 atmosphere is 101,300 pascals. I multiply by 1,000 because a kilopascal is equal to 1,000 pascals. So another way you could write that is the equivalence 1,000 pascal over 1 kilopascal. Again, pull out your calculator, and I find that I have just under 98,000 pascals. So to review, in this lesson, we've talked about average speed and average velocity, average acceleration, and pressure. This has mostly been definitions and a few calculations. For now, that's it.